We looked at things on the surface of the sun. Now we're going to go way inside and we are going to look at what's going on in the core. We are going to talk about nuclear fusion. What's the difference between fusion and fission? Well, fusion is when you take two small atoms and you fuse them together in order to make a bigger one. Fission is when you have a large atom and you break that apart to get two smaller ones. Fission is what's used in nuclear bombs, like a uranium bomb. You basically have a big uranium atom, and when you break it apart, you're going to get two smaller ones and a bunch of energy. A hydrogen bomb is when you take two small atoms, smash them together to make a bigger atom, and that's going to also release energy. So fission is breaking apart, fusion is smashing together. Inside of the core of the sun, there's about 4.5 billion kilograms of material that is fused every single second. If you take a look at Einstein's equation E equals mc squared, it tells us that energy and mass are equal if you multiply it by the speed of light squared. Speed of light squared is a huge number. So if you have just a tiny amount of mass, which atoms are a tiny amount of mass, multiplied by this huge speed of light squared, you're going to get a ton of energy. Small amount of mass, big amount of energy. This is going to come up over and over again for the rest of the year. Iron is the heaviest element that you can make in the core of a star. The reason is that stars use fusion as energy. Gravity is pulling in, fusion is pushing out. That's what's balancing gravity. Once you fuse things bigger and bigger until you get to iron, up until that point you are always releasing energy, you're always pushing out. However, when you fuse iron together, two iron atoms, that's going to absorb energy. And if you start fusing iron atoms together, it doesn't push out anymore because it's now absorbing, and gravity is going to win. That's what happens with a supernova, which we're going to get to at the end of the year. If iron is the biggest possible atom that you can make through fusion, how do we get bigger elements? There is one way, and that has to do with a star dying. Once you are not pushing out anymore, gravity is going to collapse that star down, and that collapsing down from gravity is going to smash iron together. Doesn't worry about making energy because it's not trying to fuel a star anymore. It's going to smash things down, and it's actually going to bounce back in a supernova explosion. You guys definitely need to know that iron is the heaviest element that you can create through fusion in the core of a star. Once you get to iron, you're going to start absorbing energy, and the star cannot push back against gravity anymore. The star is going to die. So that you guys can see, iron is right here at number 26 on the periodic table, which means all of these elements below 26 can be made in the core of a star. Above 26, so cobalt, nickel, copper, zinc, all of those have to be made in a supernova because you can't make them through regular fusion in the core of a star. Supernovas can create up to element number 92, which is uranium, which means all of these, as well as all of these, are man-made. You can't find them in nature. You can't find them in the universe. They're only created through artificial means here on planet Earth by humans.
If we could open up the sun, we'd see layers of dense hydrogen gas, hundreds of thousands of miles deep. And at its center, the core, the sun gives birth to light. Forged in one of the most violent reactions in the universe, nuclear fusion.
The specific nuclear reaction that powers the sun is fusion. Fusion of hydrogen into helium. You take two hydrogen atoms, you ram them together, and what's left over is a helium atom.
It sounds simple enough, but it's not.
It's actually hard to get two atoms to fuse. Two protons have the same charge, they're both positively charged, they want to repel each other.
Protons don't like to get close together. They have to come together with a huge amount of energy or velocity to get close enough to begin to fuse, and that's very, very rare.
To force protons together takes immense amounts of heat and pressure, generated by the invisible hand of gravity. The sun contains 99.8% of all the matter in the solar system. That's a lot of mass. All that mass pulls the sun together with unimaginable gravitational force.
But with gravity crushing things down, things get close enough together and nuclear fusion happens.
In this nuclear compactor, hydrogen atoms slam together 100 million quadrillion times each second. Some of these collisions are so powerful that atoms fuse, releasing energy.
When the protons come together, to bind together, they lose a little bit of mass, and that mass gets converted into energy. And every second of every day, about 5 million tons of stuff is being converted to energy. It's amazing.
Most people are going to say that fusion is two hydrogen atoms smashing together to make a helium atom, and out comes a bunch of energy. That's not quite what happens. You don't get two hydrogen atoms smashing together to get helium. You kind of do, but you kind of don't. Let me tell you what I'm talking about. Let's take a look at the periodic table. A hydrogen atom has an atomic mass very close to 1. This little 0.008 is because of a couple isotopes. We're going to get to those isotopes in a moment. If you take two hydrogen and smash them together, you're taking a mass of 1 and a mass of 1. What should you get? Crap, helium is 4. Well, where did those other two come from? That doesn't seem to make sense. 1 plus 1 does not equal 4. So you do not just add two regular hydrogens together to create helium in fusion. It doesn't work. That word isotope, what exactly is that? An isotope is when you have the same number of protons, because that's what tells you what element you have, with different amounts of neutrons, which means you're still hydrogen because you still have one single proton, but you're going to weigh a different amount because you have either one neutron or two neutrons, where the average hydrogen has none. If you don't have any neutrons, you're just called hydrogen. If you have one neutron, you're called deuterium because you have a weight of 2. And if you have 3, you're called tritium. If we take a look back at our periodic table, hydrogen has one proton with an atomic mass of 1. Deuterium has one proton and an atomic mass of 2. That's because you have this extra neutron thrown in there. And in fact, if you make water using this type of hydrogen, it's called deuterium. It's known as heavy water because it weighs more than regular water. Why? Because you have a bunch of extra neutrons thrown in. During fusion, what's happening is you have two protons that smash into one another, and instead of having two protons stuck together because they're both positively charged and they wouldn't want to do that, one of them actually turns into a neutron. It does that by getting rid of what we would call a positron, which is going to take away its positive charge, and a neutrino. Now that proton has turned into a neutron. And if you do that twice, you now have two hydrogen atoms. 1, 2, both of them have a mass of 2. Both of those hydrogen atoms are called deuterium. So now we have deuterium atoms flying around in the middle of the sun. And all of a sudden, here comes an extra neutron. Where the heck did that come from? We'll get there in a second. But when that extra neutron smashes into deuterium, what does it turn into? It turns into tritium. So now we have one tritium, we have one deuterium, and what happens? You actually get a deuterium and a tritium atom, two types of hydrogen that smash together. That's going to put these two protons together, which gives you helium, with 1, 2, 3, 4, a mass of 5. Normally, helium only has a mass of 4. And what happens is that as soon as this is created, it turns unstable. And so a neutron is going to fly out, and you're left with your normal helium atom with a mass of 4, 2 protons and 2 neutrons. Where does this neutron go? Well, I think we just learned that there's neutrons flying around. That neutron is now going to find another deuterium atom, turn it into tritium, so that you can now do fusion. So to recap, you start out with 4 protons. 2 of those protons are going to turn into neutrons. Out comes that positron and that neutrino. Now you have a deuterium atom. Here comes that extra neutron, turns one of them into tritium. Now you have tritium and deuterium smashing together, and you get your helium atom with another neutron just flying off somewhere. You have a lot of energy that comes out of this reaction. The reason that energy is coming out is because if you take a look at how much this weighs, it actually weighs less than those 4 protons that you start with. If you lose mass somewhere along the way, the only place for that mass to go is to be turned into energy. E equals mc squared tells us that mass and energy are equivalent and they can go back and forth. If you are getting rid of your mass, it's being released as energy.
It's another beautiful day in Sydney. I'm out enjoying the sun and looking to find out if anyone knows why the sun shines. So the sun gives us a lot of
Heat,
yeah.
sunshine.
Provides energy.
Yeah,
heat energy.
life, really. Where does the sun get that energy from?
I have no idea.
I have no idea.
Some kind of chemical reaction. Yeah, gas explosions.
Doesn't it burn gas?
The burning of gases.
It's burning up.
Fire.
The fire that's on the sun?
But is the sun really a giant ball of fire? I mean, wouldn't it go out after 5 billion years?
It's one of those things that you just assume you know, but then you don't actually know.
So in this bucket, I have the components of the sun. Well, I have protons and neutrons. There's some electrons, but I didn't bring them.
Okay.
Yeah. Most of the sun is actually protons.
Okay.
And so what do the protons do in the sun?
It dance together.
Okay. But when they come close, you know what they do? They just
Collide.
Well, actually, they bounce off each other. I'm coming in. Whoa!
Oh.
Why do the protons bounce off each other?
Something to do with electrons?
Positive, negative electrons. Because they don't like each other.
They don't like each other.
That's what it is.
That's because a proton needs a neutron, right?
Do you know why they repel like that?
Magnetic force.
The repelling magnet type thing.
Magnet field.
Electric field.
Positives and negative.
Positive and negative.
It's to do with the positive negatives, right? We got protons. Protons are
Positive.
So the
Positively charged.
yeah. So the positives repel each other.
Negative charge.
Okay. This is why it's so important that the sun's hot, because if the sun is hot enough, it gets these things moving so fast that sometimes they can't avoid a collision.
Okay.
And when they get too close, they actually go.
An explosion.
goes everywhere.
Wow! All right.
Smash the protons? Yeah. No, smash. Oh! And now they're stuck together. And you saw what happened when they smashed together. What happened? They leaked.
Is that energy?
Yeah.
Sick.
Well, the water poured out, but I guess energy would have poured out. Yeah.
The energy came out.
The energy came out. What was the energy before it was energy?
Kinetic energy. Stored energy.
So what's happening there?
It's releasing some mass by colliding.
And that mass is...
It's converted into energy.
It was the mass of the protons. So when the protons smashed together, they got lighter.
Yeah.
And they lost that mass, and the mass was converted to energy. You know a famous equation about that?
E equals MC squared.
Yeah.
E equals MC squared.
E égale MC2.
Have you heard that famous equation?
Which? Proton makes energy?
Well...
E equals MC squared, yes.
So what's E?
The sun, I don't know.
E is energy, M is mass, C is...
Cassidy.
Carbon? I don't remember what C means.
So C is the speed of light.
Speed of light? No. Right? Really?
Yeah.
Oh, I thought it was.
Isn't that
something
weird?
different.
The speed of light.
Right.
Ah.
Wow.
Wait, no wonder we dropped science.
It seems most people have a tough time remembering that C is for the speed of light. Maybe that's because C is a bit of a strange letter to represent a speed. In fact, in Einstein's original paper, he used the letter V for velocity of light. But nowadays, everyone uses the letter C for constant. It's a constant of the universe, the speed of light. Though some people claim the letter C stands for celeritas, the Latin word for swiftness. What is that equation telling us about energy and mass?
Energy equals constant mass.
The mass and the energy combined together create the energy.
He's basically saying, like, this mass that comes out gets converted to a lot of energy. And the speed of light is a huge number.
Yeah.
So you think about that, tiny bit of mass is a huge amount of energy. So every second, the sun is actually losing 4.3 billion kilograms. Every second. That amount of mass is being converted into
energy.
In the sun, hydrogen fuses together to form helium. But that's a little confusing because how out of only protons do we create a helium nucleus which has 2 protons and 2 neutrons? Well, the thing is, when the first two smash together, one of the protons actually emits a positron and a neutrino and quickly becomes a neutron. Next thing that happens is another proton smashes in. And again, we get more energy released. Now, if 2 particles like this collide, they emit 2 protons, and what we're left with is the helium-4 nucleus. There you have hydrogen fused into helium. And a lot of mass lost, a lot of energy released.
A lot of people used to think that the sun was a big ball of fire. Fire is a chemical reaction. You're releasing energy through bonds, molecules of whatever you're burning. So a chemical reaction versus a nuclear reaction. Let's take a look. The temperature of, let's say, a candle is about 1500 degrees. You're not going to want to put your finger in there for very long. The temperature for fusion is about 15 million degrees. It has to be much hotter. Why? Because those positive protons have to be moving so fast to smash into one another without being repelled. You have to heat things up very, very hot to do fusion. If you don't heat it up hot enough, they don't move fast enough, and then they just repel. What is burning in a candle? Well, it's wax and oxygen. You have to have oxygen in order to have fire. What's burning in fusion? It's just hydrogen. Hydrogen gas, the most abundant element in the universe. What is produced? Carbon dioxide and water. A lot of people don't realize that water is actually produced when you burn a candle. The only thing is that at this temperature, it immediately turns into steam and just goes into the air. You never see it. What's produced in a nuclear reaction inside of the sun? You take hydrogen and you turn it into helium. How much energy comes out? Well, in a candle, enough to burn your finger. In the sun, that's a huge number. That's a huge number. Fusion only happens in the core. The core is the only place in the sun where it's hot enough to get those protons moving to smash into one another. Once you leave the core, it's not hot enough and you're not doing fusion anymore. In fact, the core of a star is defined as the place where it's hot enough to do fusion. Once you cool down by moving outward and you are not doing fusion, you're technically not in the core. So the core is the only place where you can do fusion. Outside of the core, it's too cold. You might think, wait, the surface of the sun is very hot. It is for us, but it's too cold to do fusion.